Peace to all the gods and goddesses. As you can see, we in interesting times. With politics, government, the weather. You know, just everyday life problems going on. But you can see on the picture we have the sun, which from the sun, it pretty much gives us life. It gives the earth energy. Flowers, plants, animals, the energy they need to survive and grow. Before we get into it, definitely got to issue that disclaimer. This is just for research purposes, commenting, educating, just to get a different outlook on how we look at things. As you noticed, when you look up into the sky, you see a whole bunch of what they call chemtrails. As you know, them chemtrails is definitely not natural. So it's like, why are they spraying all these chemtrails? And the sun actually gives us life. It gives the trees, the animals, us energy. So why are they doing this to the sun? And as you can tell, that's not the sun that you're used to. If you're at least 30 years old, that's not the sun that you grew up with. The sun used to be like a warm orange, yellowish color, kind of like those light bulbs before they went to LEDs, the yellow light bulbs. But, now the sun's starting to intensify and it's energy. So that's why the change of color. So that's why you got that little white, bluish light, signifying that it's increasing in temperature. So hence, that's why they spraying all this stuff up there to kind of, I guess, block it out so you can kind of, lower its effect that it would have on the earth and animals and people. So we got a picture right here of Venus. And even though Venus is the second planet from the sun, it is the hottest planet in the solar system. Venus is the second planet from the sun, but is still hotter than Mercury. This is because the atmosphere is very thick and it's made up of greenhouse gases such as carbon dioxide. That kind of sounds like our environment. So then too, why wouldn't we be the hottest? Because we have more of a carbon footprint. We have all these manufacturing plants, cars, vehicles, airplanes, trains, you name it, polluting, creating carbon dioxide. And we don't have as many trees that we used to have to clean it up. So that means that carbon dioxide with the atmosphere would create same thing like Venus for it to be very, very hot. Just putting two and two together. But, with the sun, there is also radiation. So they got this thing called black body radiation. What is black body radiation? Black body radiation is the thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment emitted by a black body. It has a specific continuous spectrum of wavelengths inversely related to intensity that depend only on the body's temperature, which is assumed, for the sake of calculations and theory, to be uniform and constant. Wow, that says a lot, considering that in America, they have the race of people that they call the blacks. So it's kind of crazy how knowing that the melanin of the indigenous people around the world, it allows them to soak in the sun rays, radiation, so that's why their skin doesn't burn. So the darker they are, the more the more they're able to soak in that radiation and then in turn use that as energy. Uh, so looking down at the graph, it just shows you the Kelvin scales of temperature and the classical theory, 5,000 kelvins. It has that black line, and it's basically off the graph. And then you have 5,000 kelvins, and you have the blue curve, 4,000, the green curve, and 3,000, the red curve. I say this to say this. I bring this up, especially the movie Avatar, because there's a lot of truth in that movie about what happened to the indigenous people of this earth. So as you notice in that movie, those people were blue skin. At the same time, they also had African American hairstyles, meaning dreads, afros, braids, micros, you name it. So is that them telling us without telling us? I think so. So jumping ahead of myself. Basically, what I'm trying to say is that sun intensifying, meaning that the energy is increasing, it's getting hotter, so that the bodies that are able to absorb that radiation, the black body radiation, they're going to be able to absorb it and in turn change colors. So if you look at that graph, if you go to the far right, you have all the colors converge. You have red, green, blue, black, and they converge. Well, if you know anything about color, well, I'm from the country, so like kindergarten, preschool, first grade, we did a lot of painting, art, and I remember all that stuff, and I remember when you had the primary colors, the red, the blue, was it red, blue, yellow, red, blue, yeah, red, blue, and green, black. You mix these primary colors together, you get brown. So what I'm saying is, a lot of those Greek statues that you see, and a lot of those ancient Egyptian statues that you see that are marble and are black or black obsidian, that's telling a story. That's telling you a story of a people, a time pre-Diluvian, so that's letting you know that they was in an age of where the sun was a little bit hotter, kind of like where we're going into now. So when that sun was a little bit hotter, if you look at that graph, that black line, which with those statues are completely black, was 5,000 degrees Kelvin. So knowing what happened with religions, have the story of the Great Fall, and all this stuff. Now, using science, you can start to make sense of everything. So looking at this graph, if you have a fall, the majority of people are these different colors, and all of a sudden the energy spectrum is it fell in energy. That those wavelengths were dropped until they become one, just like indigenous people on Earth. That's how you get the colors of people. The energy was dropping. So therefore, the sun wasn't putting out as much radiation. Therefore, they didn't need those dark black bodies. So therefore, they did continue to get lighter and lighter over the decades, the years, and stuff like that, until once that cycle is starting over again, which we are in now. And so what it's doing, the sun is ramping up, and the life forms that can't take it will be burnt. Just like the good book says. But yeah, at the bottom of the graph, as the temperature of the black body decreases, the emitted thermal radiation decreases in intensity, and its maximum moves to longer wavelengths, just like I was saying. So when it moved to the longer wavelength, all those different colors, the red, the green, the blue, the black people, they became into brown people. Shown for comparison, boom, boom, yeah. A perfectly insulated enclosure with its in thermal equilibrium internally contains black body radiation and will emit it through a hole made in its wall, provided the hole is small enough to have a negligible effect upon the equilibrium. The thermal radiation spontaneously emitted by the many ordinary objects can be approximated as black body radiation. Of particular importance, although planets and stars, including Earth and the Sun, are neither in thermal equilibrium with their surroundings nor perfect black bodies, black body radiation is still a good first approximation for the energy they emit. The sun radiations, after being filtrated by the Earth's atmosphere, thus characterizes daylight, which humans have evolved to use for vision. That's why a lot of your Egyptian statues, Greek statues, are of that dark color, black marble, black obsidian. It's kind of representing the pre-Diluvian age, where people came from the pre-Diluvian era, when we had all that energy, and people could live a long, long time. So like when I showed you in that graph, the 5,000 kelvins with it black, and then the different colors, and then those colors, as energy fails, strands into one, which with all those colors together would make brown, which the indigenous people you have, and then the different shades of the color black and brown, or dark and brown. This is a LED in Kelvin's color, a little chart, so you can get a better visual depiction of basically what the sun's doing. If you look down there at 2,700 kelvins, anybody that's at least 30 years old, they know the sun looking about like that color. And then compared to what you look out and see now, it's more towards that 5,700 to the 7,000 kelvins. Okay, back to black body radiation. Black body at room temperature, 73 degrees Fahrenheit, radiates mostly in the infrared spectrum, which cannot be perceived by the human eye, but can be sensed by some reptiles. As the object increases in temperature to about 500 degrees Celsius, the emission spectrum gets stronger and extends into the human visual range, and the object appears dull red. As its temperature increases further, it emits more and more orange, yellow, green, and blue light. Tungsten filament light has a continuous black body spectrum with a cooler color temperature around 2,700 kelvins, which also emits considerable energy in the infrared range. Modern day fluorescent and LED lights, which are more efficient, do not have a continuous black body emission spectrum, rather emitting directly or using combinations of phosphors that emit multiple narrow spectrums. Black holes are near perfect black bodies in the sense that they absorb all the radiation that falls on them. It has been proposed that they emit black body radiation with a temperature that depends on the mass of the black hole. The term black body was introduced by Gustav Kirchhoff in 1860. Black body radiation, also called thermal radiation, cavity radiation, complete radiation, or temperature radiation. Black body radiation has a characteristic continuous frequency spectrum that depends on the body's temperature, called the Planck spectrum or Planck's law. It's kind of ironic, with this spectrum, because you know what they're doing with the sun, playing with that. Then how we have all these cell phone towers, and then Wi-Fi boosters in a house and stuff like that. It's kind of like it's that light code lockdown, it's a prison within a prison. And then you thinking it's, you're using it, for your entertainment, but it's really for your, let's keep going. The spectrum is peaked at a characteristic frequency that shifts to higher frequency with increasing temperature, and at room temperature. Most of the emissions is in the infrared region of the electromagnetic spectrum. As the temperature increases past about 500 degrees Celsius, black bodies start to emit significant amounts of visible light. And it's just crazy because when you think about like black people, one of the major health problems that they have is high blood pressure. So they say, But if you really understand yourself, then you would know that that's just your body going to the next level, because the doctors tell you, if you get on blood pressure pills, you're going to be on the rest of your life. How can something in your body change and then you're supposed to be on the rest of life? Maybe it's because it's supposed to happen that way. So that's what this video is, trying to help people understand who they really are and what they're made of and get ready for this shift and the change that are coming and what they're going to be going through. Viewed in the dark by a human eye, the first faint glow appears as a ghostly gray. The visible light is actually red, but low intensity light activates only the eye's gray level sensors. With rising temperatures, the glow becomes visible even when there is some background surrounding light. First as dull red, then yellow, and eventually as a dazzling bluish white as the temperature rises. When the body appears white, it emits a substantial fraction of its energy as ultraviolet radiation. The sun, with an effective temperature of approximately 5,800 kelvins, is an approximate black body with an emission spectrum peaked in the central yellow-green part of the visible spectrum, but with significant power in the ultraviolet as well. Black body radiation provides insight into the thermodynamic equilibrium state of cavity radiation. A black body. All normal matter emits electromagnetic radiation when it has temperature above absolute zero. The radiation represents a conversion, like I said, it's all energy here. Conversion of a body's internal energy into electromagnetic energy and is therefore called thermal radiation. It is a spontaneous process. You ever heard of people spontaneous combustion? Like people, it happens to people. I know you might not see that much on the news. I know you might think that's some far-fetched shit, but yes. People spontaneously combust and it burn up. So, they try to hush it. No, that was just a fire. Of radioactive distribution of, boom, boom, I guess I cut that off. Well, no, I didn't. Did I? Yeah, I did. I did. Oh, there it is. Entropy. And so that's pretty much, the kelvins, same thing I was showing you. So we're basically about between us, shit, in the middle there. So it's just keep getting hotter and hotter. Conversely, all normal matter absorb electromagnetic radiation to some degree, and objects that absorb radiation falling on it at all wavelengths is called a black body. So with melanin, people with melanated skin, so they're able to absorb the sunlight. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution depends on the temperature. Its emission is called black body radiation. The concept of the black body is idealization, as perfect black bodies do not exist in nature. However, graphite and lamp black with emissive we just forget about that because it looked like it got cut off. But in astronomy, objects such as stars are frequently regarded as black bodies, though this is often a poor approximation. An almost perfect black body spectrum is exhibited by the cosmic microwave background radiation. Hawking radiation is the hypothetical black body radiation emitted by black holes at a temperature that depends on the mass, charge, and spin of the hole. If the prediction is correct, black holes will very gradually shrink and evaporate over time as they lose mass by the emissions of photons and other particles. A black body radiates energy at all frequencies, but its intensity rapidly tends to zero at high frequency, short wavelengths. For example, now you understand why they want to do that 5G, because that 5G internet is short wavelength. So are you understanding the light code lockdown? For example, like black body at room temperature, 300 degrees Kelvins with 1 square meter of surface area will emit a photon in a visible range at an average rate of 1 photon every 41 seconds, meaning that for most practical purpose, such as a black body, does not emit in the visible range. The study of laws of black bodies and the failure of classical physics to describe them helped establish the foundations of quantum mechanics. And this is one of the main reasons why I wanted to talk about this topic today, regarding the sun radiation, and then which led us to black bodies, and now here to quantum mechanics. It's because quantum mechanics really started taking off in the early 1900s, and it was with the study of black bodies, radiation. According to the classical theory of radiation, if each Fourier mode of the equilibrium radiation is considered as a degree of freedom capable of exchanging energy, then according to the equipartition theorem of classical physics, there would be an equal amount of energy in each mode. Since there are an infinite number of modes, this would imply infinite heat capacity, as well as non-physical spectrum of emitted radiation that grows without bound with increasing frequency, a problem known as the ultraviolet catastrophe. In the longer wavelengths, this deviation is not so noticeable. In the shorter wavelengths of the ultraviolet range, however, classical theory predicts the energy emitted tends to infinity, hence the ultraviolet catastrophe. This theory even predicted all bodies would emit most of their energy in ultraviolet range, clearly contradicted by the experimental data, which showed a different peak wavelength at different temperatures. Like, damn. Like, as I'm reading this, because I didn't really read these, I just kind of screenshotted it. And, like, my head's computing all this stuff, and it's just like, damn. Calculating the black body curve was a major challenge in theoretical physics. During the late 19th century, the problem was solved in 1901 by Max Planck in a formalism now known as Planck's law of black body radiation, by making changes to Wien's radiation law consistent with thermodynamics and magnetism. He found a mathematical expression fitting the experimental data satisfactorily. Planck had to assume that the energy of the oscillators in a cavity was quantized, which is to say that it existed in integers multiples of some quantity. Einstein built on this idea and proposed the quantization of electromagnetic radiation itself in 1905 to explain the photoelectric effect. These theological advances eventually resulted in superseding of classical electromagnetism by quantum electrodynamics. These quantas were called photons, and the black body cavity was thought of as containing a gas of photons. In addition, it led to the development of quantum probability distributions called Fermi-Dirac statistics and Bose-Einstein statistics, each applicable to a different class of particles, fermions and bosons. Now, do you understand when they say they study in black matter, what is actually black matter? The wavelength at which the radiation is strongest is given by Wien's displacement law, and the overall power emitted per unit area is given by the Stefan-Boltzmann law. Shit. So yeah, y'all can just pretty much, quantum physics. So they wasn't really understanding quantum physics, so they start looking at black body radiation. So in the 1900s, October the 19th, Max Planck discovers the law of black body radiation, Planck's law, by introducing the notion of light quanta, leading in 1905 to Albert Einstein's explanation of the photoelectric effect and beginning the quantum revolution. This shit is crazy, man. December 1900, Max Planck announces his discovery of the law of black body emissions, making the birth of quantum physics. That brings us to the sun. The sun is a star at the center of the solar system, so they say. It is a massive hot ball of plasma, inflated and heated by energy produced by nuclear fission reactions at its core, so they say. Get a good look at that picture. The sun. How can I get a good fucking picture of the sun, considering it's so fucking hot, like, and that picture's so close? And this is the eclipse. So if you know anything about the sun would be that those yellow circles going up into to the left. Moon would be this one to the right, going up to the right. So they say the sun comes from the east and sets in the west, right? Whew. When you start to look at things, because here we got Venus. Now we know Venus is the hottest planet in our solar system, even though it's the second from the sun. You got Mercury, you got the sun. They say that's what the people say. You got the sun, Mercury, Venus, Earth. But yet Venus is the hottest in the solar system. And that's what it looks like. So let's go back and look at the sun. You see all those dots? Because that thing looks kind of like that. It's just the sun just looks like this energy turned up. I don't know. I don't know, man. But yeah, shit ain't adding up. Shit ain't, because that's Venus. Why does that look like the sun? I'll let you ponder on that. Well, thank you for the video. Thank you for paying attention for this long video and sticking around and learning something. Hopefully you learned something insightful that you'll pass on to the next person. So hope that you did. Like, subscribe, and get ready for the next one.